Yeah. All right. So my name is Mario Bianucci, and I am here to present Delegated Ink Trails today. So I'm going to be going over what they are and why we need them and kind of the implementation of them. So for a quick overview, first of all, we were looking, the problem that we found was that latency on the web makes inking just a very bad experience. And with remote working and remote learning growing as much as they have this year, it's really critical to have good collaboration tools. And part of good collaboration tools is a good experience using the collaboration tools. And inking is an important collaboration tool to share ideas. But it just had a very lackluster experience on the web. So that's really something we wanted to try to tackle and improve. So we found that oftentimes the browser is aware of points that have arrived after the frame deadline. So they're not actually being drawn despite the browser being aware of them. So we thought that we would be able to actually send those points to the GPU process to, after everything else has been drawn, just draw those couple last points and a trail connecting those points to the end of the stroke that was rendered. And then put that on the screen via Skia to improve the latency. And then we could even predict points further to reduce the latency even more. And the result of that was we're seeing the latency has been definitely improved, and it's making inking on the web a much better experience. And we have the future promise of OS support on this for at least Windows 10, which will drastically improve that even further. And I'll kind of touch on how that improves it a lot more later on. So first, to just give a very high-level idea of what the design currently looks like and where we're improving upon it. The pointer events will arrive from the OS into the browser process, and then the browser process queues that onto the renderer process, and they chat back and forth a little bit while the renderer process is actually rendering the stroke, and then that passes it onto the GPU process, which will draw it and put it onto the screen. It's a very, very high-level overview, but to just give you a sense of that. And then the Delegated Ink Trail API just adds a little bit of data that the renderer process tells the browser process, a little bit of data that the renderer process tells the GPU process, and then makes a new pipeline between the browser process and the GPU process to pass those points. But it's really not, other than that new pipeline, it's really not changing the execution data at all for the plumbing. And then all the interesting stuff happens in the GPU process. To give you a better feel for the timeline of events here and why we're able to improve the latency this way, here's a little timeline of it. You can imagine the browser process receives a couple input events and immediately sends them down to the CC thread to be queued. And then on the vsync, the begin main frame will occur, which sends that up to the main thread where JS dispatch will happen. After that's done, it will commit the points back down to the CC thread where it'll be drawn and passed to the viz thread. And then from the viz thread, draw and swap will occur. And then on the next vsync, the user will be able to see the actual stroke that the points produced. So this seems great. However, there's a whole frame where we know about the points, but we're not actually putting them on the screen. So you can imagine as points continue to arrive, where we have points, but they're just not being put on the screen despite us completely knowing about them and then just sitting in the queue in the CC thread. So the way that this API takes advantage of that is it still queues them on the CC thread for normal execution, but it also sends it down to the viz thread to be cached on the renderer. So after everything else has been drawn, we can draw those couple points just before swapping it onto the screen. And then as well, it was doing some prediction and things like that too, to further improve the latency. To give you an idea of how this API is used, this is just a very simple example. We wanted to make sure that the API was very, very simple for developers to use so that it's really it's not a debate on if it's worth trying to spend the time to make use of the API. It should just be very, very straightforward and simple so that they could just immediately use it without really giving it too much consideration. So all they really do is request a presenter off a new ink interface on the navigator. They give it the Delegated Ink Trail string. That's just to make it more extensible in the future. And then they give it a presentation area, which is typically going to be a canvas. This is just where the ink will show up on the screen. Then as pointer move events arrive, they render the stroke as they normally would. There's no change to how they would do that in their pipeline. And then they just make a style dictionary to describe the stroke or describe the trail that they want. So this will be the color and the diameter or the width of the trail. And then they give us the trusted pointer event in the style dictionary to the update ink trail start point API. And we take it from there to magically reduce the latency. This whole feature kind of breaks down pretty nicely into 4 chapters. So I'm going to break it up into the Delegated Ink metadata path. This is the information that the developer provides the API, how we parse it and send it to the browser, some information to the browser process and the GPU process. The Delegated Ink Point Path, which is the path between the browser process and the GPU. And then actually drawing and what we do after drawing. So the first 2 points are basically just plumbing. So I'm going to kind of blow through those pretty quickly because they're really not that interesting. I just wanted to kind of show that there's really not any change to current existing execution. I'm just adding a little bit of data here and there. But the real meat of it is going to be in drawing and after drawing. But if anybody has any questions afterwards, I'm more than happy to talk about the plumbing as well. So for the first part, as I said, is the Delegated Ink metadata path. This is what the developer provides to us, that trusted pointer event and the style dictionary, how we parse it and how we give information to the browser process and the GPU process. So the first thing that we do is we validate, parse, and transform the input that they give us. We get the actual point, the presentation area, the timestamp, the color, and the width, and get that into the viewport coordinates. And then we put that into a Delegated Ink metadata object and propagate it down to the active layer tree impl. Then we place that onto the compositor frame metadata, which will be its ride into the viz thread. But prior to what happens on the viz thread, we set a flag on the render frame metadata as well. This will be used so that the browser process can observe that and know that the API is being used. And then on the viz thread during surface aggregation, once we find the compositor frame that contain the Delegated Ink metadata, we take that off, we transform it to be in the root coordinate system, and then we put it on the aggregated frame, which will eventually put it onto our Delegated Ink point render on the renderer. So I know I kind of rushed through that very quickly, but you can see it's really not changing execution at all. It's a very straightforward path from the Delegated Ink metadata to make it into the GPU process. As far as the Delegated Ink point path goes, you'll see it's also very, very straightforward. The first thing we do is observe that render frame metadata that I mentioned to know if the API is actually being used. If it is, we set up the pipeline. If it's necessary, we only have to set it up one time. But if the API is then later used on a different tab, we have to destroy it and recreate it again. The receiver. The Mojo receiver is sent to the viz thread via the UI compositor and then binds on the Delegated Ink point render. That's where the metadata is living until rendering. And the remote end just lives on the render widget host view event handler. Then we grab the timestamp and point off that trusted pointer event. We do any transforms to the point if there's any scaling or zooming or anything. And then we send it off to Viz as a Delegated Ink point, where we'll just store it on that Delegated Ink point render in chronological order until drawing occurs. So that's all the plumbing that takes. I know I kind of zoomed right through all of that, but it's very straightforward. So we'll get into the more interesting part of it now, the actual drawing. This all happens in the GPU process. So the very beginning of drawing, very important, is to finalize a delegated ink trail very early. This is critical because in order to actually know what the ink trail is going to damage on the screen, we have to finalize the trail so that we can know which points we're actually going to use, any predicted points that we're able to create, the width of the trail, and all of that. So we have to finalize it early so we know what the damage rect of the ink trail will be. And then once we have that damage rect, we can union it into the frame's root damage rect so that we can ensure that drawing actually occurs on the portion of the screen that the trail is either being removed from or drawn onto. To get into the finalization process a little bit, the first step is to actually just filter any points that, or to filter the points to get the candidates for the ink trail, because we don't actually remove any of the old trails or any of the old points from previous trails until this step. So any delegated ink points that have a timestamp that's earlier than the metadata, so any points that arrive from the browser process with a timestamp that's earlier than the final point of the stroke that the developer provided to us, we know that that's already been rendered, so we don't need to handle it. We can just get rid of them immediately. And we know that anything that matches the metadata's timestamp or after can be part of the trail. And it's important that we do exactly match the metadata's timestamp as well, because that way the trail can overlap the end of the stroke and we can be sure that there's no gap between them or anything like that. So we just filter all the candidates. We predict any further points that we are able to. We create an SK path with the points, but we don't draw it yet. We get the bounds of the path and then expand it to make sure that we cover the full width of the stroke so that the trail is completely encapsulated. And then we set the damage rect. So there's a little bit of nuance to actually setting the damage rect. So I'm going to get into that a little bit because we actually maintain 2 damage rects. One is the old damage rect. It's caused by the damage that's in the front buffer. This is the information that's already visible to the user. It's the trail that was drawn on the previous frame. And then the new damage rect, the damage caused by the trail in the back buffer. It'll be visible to the user on the next frame. It's the trail that we just finalized, actually. And then whenever we actually retrieve the delegated ink damage rect, we just union both of them together. It's important that we maintain both of them and union them together because we want to make sure that we're removing the old frame and drawing the new frame, or sorry, removing the old trail and drawing the new trail in the same frame. If this doesn't happen, then we could end up having issues where like both of the trails exist and there's some artifacting because the old trail is overlapping the app rendered stroke, or there could be some flashing and things like that. So we have to make sure that we maintain both of them. But after finalization, there's not a whole lot else that happens for drawing. We basically just, after everything else has been drawn, we draw the path onto the SK canvas. We draw it last because we don't have any information about the actual Z index of it because, we just passed the points directly into the GPU process. It didn't go through the normal pipeline. So just putting it straight onto the top of the screen on top of everything is the best way to handle that. This also matches how the Windows 10 APIs will work. So it's good for user consistency. And then we make sure that we always reset the metadata. Even if we weren't able to draw for some reason, we want to reset the metadata so that we don't accidentally draw the same trail twice. But then after that, once the swap occurs, the trail is visible to the user. That's all it takes to get the ink trail onto the screen. As I mentioned, there's a little bit after drawing that's worth calling out. The most critical thing is just that we ensure that we force a new frame to always be drawn after a delegated ink trail has been drawn to the screen. This is typically going to be a pretty uncommon scenario because, as the point of the API is for it to extend a stroke that the app is rendering itself. But this API can be used without drawing that stroke. So if it's only being used for the trail and then the pointer goes off the edge of the window, a new frame isn't guaranteed to be drawn, and then the trail sticks around. So we want to make sure that that doesn't happen. So we force the frame to be redrawn, and then as part of that, we also have to make sure we actually union the delegated ink damage rect into the target damage rect during the next surface aggregation. This is just because if a frame wasn't otherwise going to be created, there wasn't going to be any damage to it. So nothing would be aggregated and draw and swap wouldn't occur. So we have to make sure that there's some damage on that for aggregation to actually occur. And that's the current state of things in Chromium. It's available behind the experimental web platform features flag in Canary and Dev at this point for Chrome and Edge. We're planning on doing some more experimentation to determine how much prediction we want to do, but we're really looking forward to being able to use the OS APIs because that's where the real meat of the gains will be. Because I don't have any specific numbers on the slides because I don't have super scientific results for how much this is improving the latency. Generally, I'm seeing probably somewhere in the realm of 10 to 15 milliseconds improved latency, which is definitely something to be excited about, but it's not a ton. Definitely, as I mentioned, the OS APIs is really where we see some major improvements. So to kind of explain why the OS is able to really have much more exciting improvements, I want to go back to this timeline for a moment. Because it's not totally accurate, actually. So the draw and swap occurs, and then there's that vsync. And I said that that's where the user would be able to then see the stroke that was created by those points. That's not entirely true, though, because the OS compositor typically adds an additional frame of latency then. So that's just whenever it's composing the screen, getting additional information and all of that. So really, whenever we call draw and swap, there's then another frame of latency before the user actually sees anything on the screen. And so there's really nothing we can do about that from within the browser. However, the OS APIs can do something about that. So if instead of just caching the points on the viz thread, we instead get them all the way down to the main thread of the GPU process, we can then give them to these OS APIs. And these OS APIs can wait significantly longer before actually drawing the trail because it can just wait right before the OS compositor is going to swap the buffers. until it actually draws the trail. So it can wait much longer. We can send many more points, and it can still predict points and give it to it as well. And then right before it swaps the back buffer onto the screen, it can draw the trail on top of everything. It'll look exactly the same to a user perspective, except that the latency will be drastically improved even beyond the Skia implementation. I can't give any timelines for when something like this is going to be available, but it's definitely coming in Windows 10. And we're hopeful that the results from the Windows 10 API, as well as this feature being standardized, will encourage other platforms to support a very similar API on an OS level, so we can have really good latency on all platforms. So there's a couple of open questions getting back to the Skia implementation that we're still trying to work through, and would love to get feedback or advice or comments on if anybody has any. One is that we don't know how exactly to handle clipping and transforms, particularly on the presentation area right now. If there's any overflow or clip path clips, they're just totally ignored on the presentation area as of today. So are transforms. The presentation area just always defaults to the rectilinear bounding box of whatever's provided. So if it's, if we're given something that has a circular clip on it, we just blow it up to a square, or a diamond, it's just the square that contains it. It definitely can, it can contribute to an unexpected user experience. We expect that just a rectilinear bounding box is going to be the most common scenario, but it can be an unexpected experience if inking is occurring outside of where the clip, or where something is clipped, basically. However, we just couldn't find a good way of determining what clips or transforms are applied to the presentation area whenever we're just given, the element whenever the developer is requesting the presenter. So we didn't know how to tell what clips and transforms were applied, and so for now we're just ignoring it. We don't know if that's the best way to handle it, or if doing like a best effort to apply them is going to be best, or even just totally not allowing the API to work if we think there's any clips or transforms being applied to the presentation element. We're still working through how exactly that should work, but we're definitely looking for feedback if people have specific feedback on how they think it should be handled. Another thing that we're curious about is how can we empower developers to decide for themselves if they really want to use the API. We considered having an expected improvement attribute that they could query, so that they could see how much improvement they would see, or so that they could determine how much improvement they can expect by using this API, so that they can fall back to something else if they want to. However, the problem is that that's kind of a privacy concern, especially if only Windows 10 is providing GPU support. Then, if they query it and see a really large improvement, they can assume for sure that the user's on Windows 10, and even would be able to narrow it down to the minimum version of Windows 10. So it's kind of a fingerprinting issue that we don't like. But something that recently we thought of was maybe providing the developer a way to just locally measure improvements in DevTools or something like that. We haven't investigated this a ton yet, but it seems very promising, and it might not be quite as powerful as knowing what improvement they're going to see on the user's end, but it's much safer, and will give them some ability to see how much it's providing for them. But a question that we're having a tough time answering while trying to figure out that is, why would a developer not want the API? It's very there's really no negatives that I have been able to find. It's at worst, it's going to have the latency exactly the same, and at best, it's going to drastically improve latency. So it's kind of a question of, why can't we just make this the default? Why do developers have to opt into it at all if it's as good as it sounds like it's going to be? But the problem with that is we just don't know how to determine what the width or the color of the stroke or the trail should be without the developer informing us, especially whenever you take into consideration scenarios like pressure changing the width or the color changing on the fly. It's hard to determine what exactly those would be. So I haven't found any heuristics for actually predicting that and allowing them to not have to opt in and it just be the default. But I'm very open if anybody has ideas for how that should be handled. But that's pretty much all I've got. Here's a couple links for the YCG explainer, the design doc for the overall design, and the design doc for the GPU-backed version. The GPU-backed version is not implemented at all, so now is a great time if you think you have feedback on how that should work. Now is an excellent time for you to check out the design doc and provide any feedback on that, because it's still in the design stage. But otherwise, that's about all I have, and I'm happy to open it up to questions now.
I have a few. So this seems well. To your last point, you mentioned already this isn't matching the developer style necessarily. The other thing is the developer might not be inking. So I think like for those reasons, this would always be something that you do have to enable. But anyways, the thing I wanted to ask is this is somewhat at odds with the predicted points API. Like if the developer inks over the predicted points, then we'll be drawing over that again with the OS path. I wonder if there's like some warning we should give if you're using predicted points and this API, or just accept that that's a bit of a catch.
Yeah, that's a great point. That's not something I had considered. I'm really not very familiar with the predicted points API, but it does sound like that would be something to consider there. And I think that typically we would want the developer, at least from my perspective, a developer would want to use this because it's going to be using real points rather than just predicted points. But yeah, I'm not sure of the best way of kind of informing the developer that, hey, you probably only want to choose one of those.
Yeah,
or if
that's being a DevTools thing, possibly.
Yeah, for sure. Something to keep in mind. Thank you.
I also have like lots of thoughts about clipping and stuff. Maybe we should chat later about that. But
yeah, for sure. I'd be happy to.
The other high level thing I was wondering is, could we also draw the new trail into the active buffer and not wait for vsync? Like, if you are extending the trail that was drawn last frame, it wouldn't really matter if whatever scan out happened occurred during the draw, because you're just extending a trail that was started on the previous frame.
I'm not sure that I'm totally following, because if we're drawing to the the buffer that's currently being displayed to the user, wouldn't that still need the scan out to be updated?
Right. The thing is, like, you can race the scan out a bit and possibly get part of that drawn before the previous scan out, hypothetically.
Okay, yeah, that's actually, yeah, I see what you're saying. That's a great point. I hadn't considered that, but yeah, that could definitely be a way to get a little bit more improvement on the Skia version. I still don't think that would beat the GPU back version, just because the OS can wait so much longer for the compositor. But yeah, that's definitely a way to get a little bit more improvement on the Skia version. Or it's definitely worth looking into, at least, for sure.
Mm-hmm. And you mentioned like transforms and such. Does the developer set the start point of the extended trail?
Yeah, that as part of the API, and I can go back to the example page. But part of the API is they give the trusted pointer event, and that's intended to be the final point of the stroke that they're drawing. So they render that stroke, or they render the stroke for that pointer event that they just received, and then they just give it directly to us, and that's intended to be the final point of the stroke they rendered and the first point of the trail.
Do you think that there are many use cases for this not being the actual point on the screen at which the pen is?
I can't say. That's a good question, but I can't really say for sure. We did intend for this to be only trusted pointer events, so if they do transform it, I don't think that there would be a good way for us to handle that unless we open it up to not trusted pointer events. I can't imagine that that's a very common scenario, but that's not to say it doesn't exist. It can absolutely exist somewhere. It seems a little bit strange for the ink to show up and not aligned with the user's finger or pen or whatever.
Yeah, and I think you lose some of the benefits of predicting. Like if it's not directly under your pen, you're less likely to notice latency.
Yeah, that's very true as well. There was a comment.
I think the comment was, "This is a cool discussion."
I appreciate the comment. Okay, so yeah, Sarah's saying we're at time. So thanks everybody for attending, and definitely ping me on Slack or email me if you have any questions or want to discuss anything. I'm excited to talk about whatever you're interested to talk about. Thanks, everyone.